This video we are going to discuss about part 2, surface chemistry part 2. Okay, look here, you have here three pictures are given here. Observe this carefully. Okay, what you can see here, what are the difference here? All of them are mixture, but they have some difference. Okay, so in this slide we are going to discuss more details about this. So see here, all of them are solution, all these three are solution. Okay, so we can classify this solution here. One is clear solution, one is clear solution. The first one, it is clear solution. Okay, and second one, it is suspension, and third one, it is colloid. Okay, one is solution and another one suspension, then it is colloid. We know pure solution. Solution mean there is solid and there is solute and solvent. Solute homogeneously dissolved. It is homogeneous mixture. Solute dissolved homogeneously. Homogeneously dissolved mean we cannot see solute particles. We cannot see solute particles. Also solute particles cannot separate by filtration. Size of solute particles very small. Okay, examples such type of solution, sugar solution, salt solution. These are example for solution. Okay, second one there is suspension. Suspension particle size is bigger, more than 1000 nanometer. The previous one solution, here size of the particles, it is 1 nanometer or less than 1 nanometer. Size of the particles very small in solution. That's why size of the particles cannot separate. But here suspension it is heterogeneous mixture. So, solute particles not homogeneously dissolved. Okay, so we can see solute particles with our naked eye. No need any microscope. Without any device, we can see solute particles in suspension because size of the particles bigger, more than 1000 nanometer. Size of particles are bigger. That's why these particles of suspension can be separated by filtration. Example for suspension, sand in water. Sand, we can separate sand from water. So sand in water, it is example for suspension. Suspension, it is heterogeneous mixture. Okay, size of the particles more than 1000 nanometer and it can separate by filtration. Example, sand in water. Third one we have to discuss here. Third one, it is colloid. Okay, so in this chapter we have to study more details about colloid. We are going to study about colloid. So colloid also heterogeneous mixture. So only pure solution homogeneous mixture. Rest of this two, it is heterogeneous mixture. Okay, suspension and colloid are heterogeneous mixture. Size of the particles between 1 to 1000 nanometer. The first one, size of the particles 1 nanometer. Second one, size of the particles more than 1000 nanometer. Third one, size of the particles between 1 to 1000 nanometer. That is colloid. Okay. Also here, particles cannot separate by filtration. We can see particles, but particles cannot separate by filtration. Here only in suspension we can separate particles, but in homogeneous solution and colloid, particles cannot separate by filtration. Also remember, suspension and colloid, they are heterogeneous mixture. Okay, example for colloid, butter, jelly, these are example for colloid. In colloid there is two terms, dispersed phase and dispersed medium. You know, in solution there is solvent and solute. In solution there is two terms, solvent and solute. Similarly, we have here dispersed phase and dispersed medium. When you take sugar solution, when did you take sugar solution? Okay, sugar in water, that is sugar solution. So here water is solvent is water, solute is sugar. Okay, sugar in water, that is sugar solution, solvent water, solute sugar. Similarly, when you take a colloid, there is dispersed phase and dispersed medium. Dispersed medium mean like solvent. Okay, here solvent, we will say dispersed medium. Dispersed phase mean like solute. Here solute, we will say dispersed phase. Okay, so these are the things. Here colored glass is one example for colloid. Colored glass, it is example for colloid. In colored glass, dispersed phase and dispersed medium both are solid state. Another classification of colloid. Okay, based on the interaction between dispersed phase and dispersed medium. We discussed dispersed phase and dispersed medium. The type of interaction between dispersed phase and dispersed medium, we can classify colloid. There are two different type of colloid based on this: lyophilic colloid and lyophobic colloid. Lyophilic colloid and lyophobic colloid. Lyophilic colloid mean the interaction between dispersed phase and dispersed medium is higher. Higher interaction between dispersed phase and dispersed medium, or you can say greater affinity between dispersed phase and dispersed medium. Such type of colloid is lyophilic colloid, and these colloids are highly stable. No need any stabilizer, no need any chemicals to stabilize such type of colloid, lyophilic colloid, because they have greater affinity between lyophilic dispersed phase and dispersed medium. Okay, and here different points. These colloids are not reversible. Okay, when you separate dispersed phase from dispersed medium, you cannot make colloid again by simple mixing. Okay, that's mean this type of colloids are not reversible. After separation of dispersed phase, you cannot make colloid again by simple mixing. That is lyophilic colloid. Okay, also we discussed no need any particular chemicals to stabilize this type of colloid. It is highly stable. Also it do not easily coagulate. This colloid do not easily coagulate, not easily precipitate, or not easily coagulate. Okay, example for this type of colloid: gum, gelatin. These are example for lyophilic colloid. Look here, another one, lyophobic colloid, just opposite of lyophilic colloid. Lyophobic colloid means there is very less affinity between dispersed phase and dispersed medium. Less affinity, or you can say no affinity between dispersed phase and dispersed medium. Okay, and here these are not reversible. Here this is reversible. Okay, lyophilic colloid, it is reversible after separation. After separating dispersed phase, you can make colloid again simple mixing. That is, it is reversible, but it is not reversible. Lyophobic colloid, this is lyophobic colloid, it is not reversible after separation of dispersed phase. By simple mixing, you cannot make again colloid after separation, after precipitation. Precipitation means from colloid we separate out dispersed phase like a precipitate. That is, after precipitation we cannot make colloid again by simple mixing. That means Leophobic colloid not reversible, leophilic colloid reversible. Okay, and here we discuss it is highly stable, stabilizer not required. But here leophobic colloids are very less stable. It needs some stabilizer. It needs some chemicals to stabilize this type of colloid. Okay, and here another one. Here you can separate dispersed phase very easily. You can separate dispersed phase very easily after adding suitable electrolyte. But in this case, here separation of dispersed phase is hard, not easy. But here it is very easy to separate dispersed phase because very less interaction between dispersed phase and dispersed medium. So we can easily separate dispersed phase. Okay, by adding suitable electrolyte. Example for leophobic colloid, solution of metals like silver and gold. Example for leophobic colloid. Example for leophilic colloid, gum or gelatin. Gum and gelatin are example for leophilic colloid. Okay. Okay, so here next one, classification of colloid. Okay, based on the type of the particles present, again we can classify colloid. There are three different type of colloids based on the type of particles, type of dispersed phase. Okay, here first one we have to understand here macromolecular colloid. First one, macromolecular colloid. Macromolecular colloid means this colloidal particles. In macromolecular colloid, colloidal particles are bigger particles. These bigger particles on disintegration, on breaking down and forms colloidal particles. Macromolecular colloid mean here it is particles like polymers, okay, large molecule. This large molecule after breaking down it forms smaller molecules with diameter 1 nanometer or colloidal particle will be formed. Example for this type of colloidal particle: starch, protein, nylon, polystyrene. These are polymers. Okay, these polymers in suitable dispersed medium, it will disintegrate, it will break down and form colloidal particles. Clear? This is macromolecular colloid. Next one, multimolecular colloid. Multimolecular colloid mean here colloidal particles very small, less than 1 nanometer, very small molecules. In dispersed medium, these colloidal particles, these particles will aggregate. It will join to form colloidal particles, okay, with diameter more than 1 nanometer or 1 nanometer. Okay, so here these two are just opposite. Macromolecular colloid mean here colloidal particles are bigger and it break down and form colloidal sized particles. You understand? Here particles are bigger like polymers and it will break down to form colloidal particles. Here already particles are very small. Its size less than nanometer. It is not colloid. Okay, very small particles. But these very small particles join to form colloidal sized particles. That is multimolecular colloid. Multimolecular colloid example: gold salt, sulfur salt. Okay, here sulfur salt S8, sulfur salt, gold salt. These are example for multimolecular colloid. Clear? Next one, associated colloid. Associated colloid means substance at low concentration it acts as electrolyte. At lower concentration, at low concentration it acts as like electrolyte. But higher concentration it behave like a colloid. At higher concentration particles will aggregate and form colloidal size particles. Such type of substance, such type of colloids are called associated colloid. Okay, example for associated colloid: soap. Soap, when you mix soap with water, it produces miscellaneous. This miscellaneous example for associated colloid. We will study more details about miscellaneous. Okay, so here we discussed multimolecular colloid. Here bigger particles breaking down to smaller colloidal particles, that is macromolecular colloid. Example, starch, protein, nylon, polystyrene. Multimolecular colloid, very small particles, particle size less than 1 nanometer, they aggregate to form colloidal particles. Okay, and here example, gold salt, sulfur salt, these are example for multimolecular colloid. Third one here, associated colloid. Associated colloid means colloid substance, it behave like electrolyte at low concentration, but at higher concentration, it acting as like colloid. Example here, soap produce micelles. You understand? Okay, we discuss micelle formation. Micelle is example for associated colloid. Okay, so we have to discuss here more details about micelle formation, mechanism of micelle formation, etc. Okay, look here, we know soap. Oil or fat reacted with the sodium hydroxide, it forms soap. This process is called saponification. Actually soap, the molecular formula of soap represent like this: sodium stearate, stearic acid here, sodium stearate. This sodium stearate, after ionization, it form stearate ion. This is stearate ion and Na plus. Stearate ion and Na plus. Here you understand here, this is soap. There is hydrocarbon. This part is hydrocarbon. This part is hydrocarbon and this part is polar. This is non-polar region. This is polar region. This is soap. So look here, two end here, this is hydrocarbon, it is non-polar, and this part it is polar. Clear? Here this polar part, it is hydrophilic part. Hydrophilic means this part will attract water molecule. Hydrophilic means it will attract water. That is hydrophilic. Hydrophobic means it will repel with water molecule. That is hydrophobic and hydrophilic. So soap, there is two part. Okay, non-polar part and polar part. Polar part, it will attract on water molecule, it is hydrophilic, and hydrocarbon part, it will repel with water molecule, it is hydrophobic. Clear? So this is the information here, okay, about soap and structure of soap. Okay, and here let us discuss here the cleaning action of soap. How soap helping for cleaning. Look here one cloth, there is some grease or oil or something. Okay, we put this cloth with the soap. So we know soap molecule, there is two end. One end it is hydrophilic part and another one hydrophobic part. You know, oil or grease, it is hydrocarbon. Okay, and this hydrocarbon part, also soap, there is hydrocarbon part. Oil or grease, it is hydrocarbon. Also soap, there is hydrocarbon. These two end will be attract with the van der Waals force of attraction. Okay, so here this structure represents soap. Okay, this represents soap, and this negative part represents polar part. Okay, here we know soap, here C17H35 COO minus. Okay, so it is just like this. Here COO minus, here at the end negative charge, that's why we represent here negative charge. And this part, it is hydrocarbon. This is hydrocarbon. This I did here. So oil or grease attack on hydrocarbon. They will attract on hydrocarbon, and this part will be non-polar part, and it will attract with water molecules. Clear? Okay, so after that it will change like this. See here, this is oil or grease. Okay, all hydrocarbon part of the soap will be attract on oil or grease, and here these are the polar part. This polar part, it is hydrophilic part, and it will attract on water molecule. Okay, then this oil or grease moving away with water. This here soap helping for cleaning. Okay, so I will repeat once again here, cleaning action of soap. Here this is the cloth, there is oil or grease. Oil or grease, it is hydrocarbon. When we put this in soap which contain hydrocarbon, this hydrocarbon part or hydrophobic part of soap will be attract on oil or grease. Okay, and after that it form micelle. This is the micelle. This structure is called micelle. Okay, this is the enlarged structure of micelle. Okay, here in the middle there will be oil or grease, and all hydrocarbon part will attract on oil or grease. Okay, all hydrophobic part will be away from this. This structure is called micelle. This micelle formed, it will move away from the cloth with water molecule. Thus this soap helping for cleaning. Okay, this micelle formed, this formation of micelle will take place at a particular temperature. Okay, it need a particular temperature. This particular temperature is called Kraft temperature. Kraft temperature, or you can say TK. So here, what is Kraft temperature? The formation of micelle takes place at a particular temperature. This temperature is called Kraft temperature. We can represent TK. Okay, and another one, formation of micelle takes place at a particular concentration. Soap, it need a particular concentration to form micelle. That particular concentration is called critical micelle concentration, or we can represent CMC. CMC means formation of micelle. Formation of micelle takes place above particular concentration. This particular concentration is called critical micelle concentration. Okay, these are the things we discussed here. Formation of micelle. I will repeat once again. This is the structure of soap. Soap on ionization, it forms C17H35 COO minus Na plus. Okay, so there is this structure, we can say this is soap. Okay, this is polar part, this is non-polar part. Non-polar part, it is hydrophobic, it will repel with water molecule. Hydrophilic part, it will attract on water molecules. Okay, cleaning action of soap. Here oil or grease, when we put with soap, all hydrophobic part will attract on oil or grease, and all polar part mean hydrophilic part, it will be away from the oil or grease. Thus micelle formed. This micelle formed, it will move away from the water, and it helping for cleaning of cloths. Clear? Prepare colloid. There are different steps, different methods to prepare colloid. First one, we have to discuss here chemical methods to prepare colloid. Okay, look here, different chemical methods, different chemical reaction to prepare colloid. First one, oxidation. Okay, oxidation, generally sulfur salts are prepared. Sulfur salts are prepared by oxidation. Look here, hydrogen sulfide reacted with Br2 form hydrogen bromide and sulfur salt. Hydrogen sulfide reacted with oxygen. Here water formed and sulfur salts are formed. Here sulfur is oxidized. Okay, so this is oxidation method to oxidation method. So remember, in example for preparation of salt by oxidation, sulfur salts are prepared by oxidation method. Okay, look here, after oxidation, next one, reduction method also using to prepare salts. Okay, generally metal colloids of metals like gold salt, platinum salts are prepared by reduction. Gold chloride reacted with the tin chloride, it formed tin chloride and here gold salt. Another one, platinum chloride reacted with the tin chloride again formed and here platinum salt. Okay, so this is example for reduction. So remember here, sulfur salts are prepared by oxidation, metal salts are prepared by reduction method. Okay, third one, here third one, preparation of colloid by chemical reaction. Third one, double decomposition. Okay, here arsenic oxide reacted with hydrogen sulfide. Here arsenic sulfide formed. Arsenic sulfide, it is colloid. Arsenic sulfide, it is colloid. Okay, so this is double decomposition. Both arsenic oxide and hydrogen sulfide both decomposed. So double decomposition happened here. So here arsenic sulfide colloid formed. Next one, hydrolysis, addition of water. Here ferric chloride after hydrolysis it formed ferric hydroxide, iron hydroxide. Okay, here iron hydroxide, it is colloid. Okay, this colloid formed by hydrolysis. So these are the different methods to prepare colloid: oxidation, sulfur salt, reduction, metal salt, double decomposition. Here I told you example arsenic sulfide. Hydrolysis, here I told you iron hydroxide colloid formed by hydrolysis. Clear? Second method of preparation of colloid, it is peptization. Peptization means freshly prepared precipitate changed to colloid by adding suitable electrolyte. This method is called peptization. We have some freshly prepared precipitate. This freshly prepared precipitate convert into colloid by adding suitable electrolyte. This method is called peptization. See here example for peptization. We have precipitate of iron hydroxide, FeOH thrice. This is precipitate. When you add FeCl3, you just add FeCl3. From FeCl3, Fe3 plus interact with a different precipitate. Okay, and it will change to colloid. Actually, imagine this is one FeOH thrice. This is one precipitate. This is another precipitate. This precipitate stay together. It will stay together. Normal case here, it will stay together. But when you add FeCl3, in FeCl3 there is Fe3 plus. This Fe3 plus. Okay. So here one precipitate, it will absorb Fe3 plus. It will absorb Fe3 plus. This I am showing here like this. One precipitate molecule, it absorb many Fe3 plus molecule. Okay, this positive one precipitate surrounded with different Fe3 plus. This I shown here, one molecule with a different positively charged particles. Same thing happening here near to this precipitate molecule, another precipitate molecule also absorbing Fe3 plus. Okay. Now here this is one precipitate molecule, this is another precipitate molecule, each molecule surrounded with a positive charge. Okay, so same thing happening in all precipitate molecules over here. Okay, so different molecules surrounded with positively charged particles, so they have opposite charge and these molecules will repel each other. These molecules repel each other because all the molecules have same charge. That's why these precipitate molecules do not settle down. It will uniformly distribute throughout the solution uniformly distribute throughout the solution. Finally, it will change to colloid. This process is called peptization. I will repeat once again. Here, this is one precipitate molecule. It will absorb Fe3 plus. Okay. Now this is one precipitate molecule surrounded with many Fe3 plus. This is I shown here, one precipitate with many Fe3 plus. Same thing happening another adjacent precipitate molecule. Okay, same process will happen throughout the precipitate, throughout the solution. All the precipitate molecules getting positive charge. We know similar charge will repel each other. That's why precipitate molecules will be distributed throughout the solution. Okay, it will move throughout the solution. Finally, precipitate change to colloid. Okay, so to convert freshly prepared precipitate to colloid, we will add suitable electrolyte. This electrolyte is called peptizing agent. Okay, this process is peptization. Okay, for peptization we will add suitable substance, suitable electrolyte. That's why we will call this peptizing agent. Okay, so this is the process of peptization. Another method to prepare precipitate, it is electrical disintegration or Brady's arc method. Electrical disintegration or called Brady's arc method. This Brady's arc method used to prepare salts or colloids of platinum, silver, gold, copper. Okay, Brady's arc method used to prepare colloids of silver, gold, platinum and copper. Okay, this is the apparatus arrangement to produce this type of colloid. Okay, there is one container. Okay, this container, inside this container there is another container. This another container is kept on the ice cube. Okay, and here there is two electricity through these electrodes. There will be one electrical arc will be produced in this dispersed medium. Look here, this is dispersed medium, these are electrodes, and here this showing ice cubes. When we pass electricity, these electrodes will be vaporized and this vapor will be dissolved in dispersed medium, and this dispersed medium finally changed to colloid. Clear? Thank you for watching this channel. Please subscribe and press the bell icon for more videos. Thank you.